So welcome everybody to our second talk for the day. We have speaking Digjoy Paul talking about a multiset generalization of set partition algebra.
Thank you, Laura. It's my pleasure to part of this conference. Thank you, the organizers. Now I will be talking about joint work with Siddha Narayanan and Shraddha Srivastava. So it's about multi-set generalization of set partition algebra. Okay. Yeah. So here is the plan for my talk. So before I start, please feel free to stop me if I go fast or if you have a question. Okay. At first I will recall what is classical Survival duality, and then partition algebra, then our generalization of this partition algebra, multi-set partition algebra, and then some relation from this new diagram algebra, multi-set algebra, to the previous one, and upon building on that result, we will be showing cellularity and semi-simplicity property. And if time permits, I will talk about the connection between this multi-set tableau, placism, and restriction problem. Okay. Yeah. So the story begins at beginning of 20th century when Sur was writing his thesis. So he took the group of invertible matrices GLNC and the symmetric group on K letters. So you know that the invertible matrices acts on the vector space Cn by matrix multiplication, and so it works diagonally on the k-fold tensor product of the space, right? And on the other hand, so if I were to say the action, then you take some element ei1 tensor up to eik. So these are the E1 to En is the standard basis of Cn, and each matrix of GLNC that acts on each factor A ei1 up to A eik, and the symmetric group on K letters permutes the position of the tensor, right? And his remarkable observation was that these two action commutes, and there is a surjective homomorphism from the group algebra of symmetric group to the centralizer algebra of GLNC. So this space is nothing but the set of or group of all intertwiners. So these are all operator from Cn tensor K to itself, which respect the GLN action. Okay, these things called centralizer algebra. So he find a onto homomorphism between these things, and this homomorphism is isomorphism once n exceeds the value k. Okay, and this is the rich source of many combinatorial and representation theoretic aspects. Like many properties of the one algebra or one group can transfer to the other via this Survival duality. Like you can study the centralizer algebra via the group via the representation theory of symmetric group. Okay, and this algebra we call it a diagram algebra. And the reason behind this is a diagram algebra is a finite dimensional algebra which has basis consist of some diagrams, and the multiplication rule is governed by some concatenation on those diagrams, right? So suppose for simplicity I take the reflection 1 2 in the symmetric group, right, and suppose in S3, and I multiply with the same here, and what is the rule then? So you first of all you can represent first the permutation 1 2 in a two-layer diagram. So I first wrote here the vertices here 1 2 3 and again 1 2 3. Now to represent the permutation 1 goes to 2, I draw the line from the upper level 1 to the lower level vertex 2, and for the other thing I repeat the same. And so I take two diagram here, and to define the multiplication, what I have to do, you have to follow the path on this diagram. So you can place one diagram above another, and you can follow you can identify the middle vertex 1 2 3, and you will get the identity matrix. 1 goes to 2, 2 goes to 1, so this gives me 1 to 1, right? So symmetric group algebra gives one prototype example of diagram algebra. So one extension is the you can represent a set partition diagram, set partition of a set in terms of a diagram. Like suppose you consider a set partition of 1 2 3 and 1 prime 2 prime 3 prime. Sorry, yeah, 1 2 3 1 prime 2 prime 3 prime, and you take a set partition. So 1 2 1 prime 3 and 2 prime 3 prime. This is a set partition of this, and you can represent this in terms of this diagram. So you place 1 2 3 on top and 1 prime 2 prime 3 prime on the bottom, and each of the block or set partition you can represent like a block. So like in the red 1 2 and 1 prime, I connect 1 and 2 on the top, and it's connect to the bottom 1 prime, and I follow the rest the similar way. So these are set partition diagram. So after this classical pseudo duality, so then in 1992, Von Jones and Martin, they extend this pseudo duality relation to, so instead of GL and C, they considered the subgroup symmetric group Sn. So remember the Sn lies inside GL and C as permutation matrices, right? And on the other hand side, they are looking for the similar algebra which will play the role of symmetric group algebra in the classical sense. So what they find is they defined a algebra based on those set partition diagrams, and they find a onto homomorphism from one algebra to the centralizer algebra of the other. And this homomorphism is isomorphism when n greater or equals to 2k. Okay. So this is a variant of pseudo duality, and since this pseudo duality is there, so the combinatorics of symmetric group Sn and the combinatorics of partition algebra, they flow from one side to the other. Okay, and some of them we may probably talk about in the later half of the talk. Okay, so first, how this partition algebra is diagram algebra. So you have one diagram, one set partition. So I considered here the set 1 2 3 4 and 1 prime 2 prime 3 prime and 4 prime, and I took a particular set partition 1 prime 2, this is one block, 3 is one block, 4 is one block, then 2 prime to 3 prime is one block, and 4 prime is the other block. And if I say this is my first diagram, if I say this is my first partition diagram, set partition diagram, and the second one is just the second one also I took some else, and to define the multiplication, there is a beautiful formula. So it says that like before, you can identify the middle vertices, these prime and unprimed vertices in the middle. Then you concatenate, you follow the path. You follow the path, right, from 2 1 to 1 prime. Then you come to 1 and follow the rest. So hence you will be having here this block. And these 3 and 4, there are nowhere to go, so they'll be sit here, and same for these 3 prime and 4 prime. But look at the middle, these 2 prime and 3 prime, and these 2 and 3, when they are joined, when they're identified in the middle, they becomes a block which is not connected to the top row and not connected to the bottom row of the second one. And similar things happen when 4 prime and 4 are identified. So the multiplication rule is defined like you take two diagram pi and some pi prime, then the pi star pi prime is, so this xi is a variable, and xi to the power something, this is number of connected component that lies totally inside the diagram, like totally in the middle. So here are this is my first thing and this is my second thing. So here 2, and the rest is the concatenation of those two. So this is the multiplication rule in partition algebra, and this basis consists of these set partitions diagrams is called diagram basis. Okay. Now from this setting, we ask the following question. So look, for the partition algebra, we have the basis as set partition diagrams, and to represent, we have distinct vertices on the top, distinct labeled vertices, and on the bottom. Now question is, suppose you want to repeat some of the vertices here. Like instead of single one, if I put 1 and 1, and 3 is also repeated, right? And I can construct such a diagram. Then that represents a multiset. So multiset is a collection of objects which may repeat. So this 1 1 2 1 prime, this is a multiset. 3 1 prime 2 prime, this is set, right? So together, if I allow to repeat the sum of the vertices in the previous setting, what I get is a multiset partition of a multiset. Now, like we generalized from the symmetric group algebra to set partition algebra, now we ask, can I further generalize it? Can I build a algebra based on these multiset diagrams?
There is
okay.
There is a question in the chat if you are allowing non-nesting on crossings. Like, are you allowing in the diagrams to cross or to nest?
Okay, so as long as this one block determine the same multiset, they will be identified. They will be same. Like I can join 1 1 2 to 1 prime via this line or this line or this line. So all these three possible things are there. So I can choose any one, and I fix that. So like if I say that I always join the top thing to the bottom from the last vertex.
Could you have?
Then
Could you have an element that contains the 3 prime, the first 3 prime on the bottom, like 1 1 2 1 prime and 3 prime? Will that be as an element in the algebra?
Sorry, can you repeat what you said?
Yes. Suppose that I want to include in one of the sets the 3 prime. So I want to have 1 1 2, the 1 prime and the 3 prime. That would also be an element in your algebra.
Right.
Okay, thank you.
Yeah. Means if there is some doubt, so it will be clear in coming slides. No problem. Okay, so if I pose the question in in algebraic setting, then what I was asking is, so for the partition algebra, you had homomorphism from 1 to the centralizer algebra of symmetric group Sn acting on the space Cn tensor K. So now instead of Cn tensor K, if I take the symmetric tensor, K symmetric tensor, sim K Cn, and I, as usual, I fix one side, I take the same action of Sn. Find it that as GLN act on Cn, and all these actions are coming from that restriction GLN to Sn. And on the other hand, I am searching for one algebra which will play the role of partition algebra in this setting. So there's I want to define algebra which give me onto homomorphism to the centralizer algebra of symmetric group Sn acting on symmetric tensors, right? And more generally, what we can do, you take sorry, you take a vector of non-negative integers lambda, and you define the sim lambda to be the tensor product of the individuals, and you ask the same, that you one side you have the Sn action, and on the other side you want something, and hence we are asking this thing. And so we asked the question in twofold way, combinatorially and algebraically, and it is the same question, and that is what I'm going to talk about now. So given such a lambda, and we are considering multiset partition of the multiset this. So this means 1 power lambda 1 means 1 repeat lambda 1 times, 2 repeat lambda 2 times. So based on such multisets, we want to define a algebra, and also want to define a multiplication rule, so that algebra fills the question mark in these two previous setting. Oh, sorry, I am going forward. Okay, so for that thing, the first step is to realize one multiset partition diagram in an alternating form. So this is the first presentation. This 1 1 is here, 2 1 prime 2 prime is this block, 1 prime is the singleton. So alternatively, what I'm doing, we are considering a graph whose vertices are of the from a comma b such that 0 less than a less than 2. So since the first part is 2, and b is less than equal to 0, is equal to 1. So all 0 0 0 1 1 0 1 1 2 0, and the same on the bottom. Okay, now I will define, construct a bipartite graph out of it. So like, suppose I want to construct this this block 2 1 prime 2 prime. What I will do, I will take this 0 1 edge from the 0 1 vertex and this 1 1 vertex, and that will give me, means that is represented by this. And how exactly it is, because this 2 1 prime 2 prime, if I write in that way, that 1 power something, 2 power something, 1 prime power something, and 2 prime power something, so means that this is the multiplication. If I write the same thing in terms of this power notation, then I'm getting for this unprimed letter 2, I'm getting here the pair 0 and 1, and from this 1 prime 2 prime, I'm getting 1 1 as the powers, and I would join that. Okay, so in this way, given a multiset, each block I am representing it in terms of a edge, and I define the weight of edge is the tuple of vertices joined by them. Like weight of that edge E is the 0 1 comma 1 1. So see that since we are considering here the multiset partition for the vector 2 comma 1, so the total thing should be 1 square 2 power 1, 1 prime power 2, 2 prime power 1. So the total weight of the gamma, as I defined, this is the sum of the weight of the edges, and that should be always gamma comma lambda. Okay. So given a multiset M of a multiset, I first represent in terms of this diagram. You can forget this diagram also. What I am doing from this multiset, I'm constructing a bipartite graph, and it is a multigraph because more than one. If two blocks are same, then there will be multiple edges between that two vertex. So it is a multigraph, and I put a weight on the edges and hence on the total graph. So I am getting a bipartite multigraph of weight lambda comma lambda. So this is the first construction that we did, and on next slides I will define the multiplication out of these bipartite graphs. So for simplicity, suppose I take lambda equal to only one parts, that is 2. That means we are looking for graph built on vertices 0, 1, 2, so that the total weight of the graph is 2, 2. So I start with a multiset partition. Is 1, 1 prime, 1, 1 prime. So since one part is 2, so I am looking for multiset of this 1 power 1 comma 1 comma 1 prime comma 1 prime. Right? I have only one part, so 1 power lambda 1, 1 prime power lambda 1. That is the thing. So this is one multiset, and I represent it like this one red. This is no unprimed attached, so this is attached to 0 in the bottom. This 1 prime, no unprime is there, so I do it here, and this 1 and 1 prime is the parallel edge from 1 to this, right? And to define the multiplication on this diagram, I will be speaking roughly the rule. So suppose you take two diagrams, then like before we want to define something concatenation. For that you add n minus 3, so there are 3 edges, non-zero weighted edges. So you add n minus 3 0 to 0 fictitious edges on the top and the bottom. Then we will look forward for different path configuration. So what I called a path configuration here is, so suppose you have two vertex the same graph, you add first here the 0, 0 edges, and here also 0, 0 edges. Now you follow the path, right? Suppose what I am meaning by a path configuration, suppose I explain this one, how I got this. So from 0 to 1 come this way, and then you identify the middle. Then from this junction 1 you have two possibilities, 1 to 0 or 1 to 1. So if I take 1 to 0, 1 to 1, then I am following this. If I am taking this is 0 to 1 and 1 to 0, so this one, right? This one. And at the same time, if I take 1 to 0 and identify the middle and come back here, then I have the green one, and for the red you go just parallelly 1 to 1, 1 to 1, you have this one, and see the rest of the things are 0, 0 edges, 0, 0, 0 parts. Is it clear? The first configuration?
Yes, I think so.
Okay. So similarly, we look for the different different configurations, and in this case, we have 4 configurations, and to each from this path configuration, I want to construct I want to collect two data. One is the resultant graph gamma, and the other thing is its coefficient. Like first to get this resultant one graph gamma, what I do, I just ignore the middle one. So you take a path here, then first you ignore the middle here, then you are having a graph, a bipartite graph whose edges are 0 to 0 0 0 0 up to 0 0 and then 1 1 1 1, and that graph is presented here, yes, 1 to 1. Probably have written n minus 4 here. Okay, and to get this coefficient, what you have to do, so first you fix this top and middle vertices 0 to 0 and find the all possible permutations of the middle vertices. So like there are n minus 3 zeros and n minus 3 zeros and all ones and 1 so that gives me n minus 4 as counting, and from 1 to 1 and 1 to 1, if I instead of going via 0 1, I may have go via 1 and 0. So there are two possibility, so that's give me 2, and from this thing I can have all 0 0 1, then 1 can jump to the rest of many places, and that gives me n minus 4, right? So this is my formally the rule, and if I follow to the each graph, each path configuration P, I am having a multiplication rule, and by formalizing this thing to variable xi, we define a multiset a algebra based on these bipartite graphs whose structure coefficient, this one, these things, they are polynomial in xi. So this is the main construction of the algebra. You start with multiset partition of a multiset, you represent them in terms of bipartite graph, then you define a concatenation rule on that bipartite multigraphs, and we prove that the resultant thing gives a, and since the structure constant is a polynomial, and we prove that that gives a finite dimensional associative algebra, and which is unital as well. Okay, and so the next thing maybe I can or skip for the moment, and we prove a new Surreal duality between this algebra. We call that multiset partition algebra and the centralizer algebra as desired. We prove that this homomorphism is isomorphism when n exceed twice the size of lambda. And now we are asking that what is the relation, what is the connection of this new defined algebra from the previous one, like the partition algebra. So we are about to find a connection between mp lambda n and pkn, and hence on the good case relation between these. And for that thing, the natural way was you take a basis of mp lambda n that consists of multiset partitions, and you have the basis of partition algebra that consists of set partition diagrams. So if I were to define a embedding from this mp lambda n to pkn, I have to, if I can give a relation from this basis to basis, there is a chance. So
Joy,
yeah.
This is the 2 minutes warning. You have 2 more minutes.
Okay, sure. Okay, no problem. So what we're giving here is that you take a multiset partition like 1 1 1 prime and 1 prime, associate it to a class of partition diagrams, and the construction and the map is also very easy. You can represent a multiset partition diagram in different way, or or you can obtain one diagram like this and you can permute those. So you have two diagrams. So basically we give a bijection between multi-set partitions and a class of set partitions diagrams, and the final embedding is you take the input multi-set partitions and send it to some class of diagrams, and this x comma phi, these are actually known as some this one maybe I have skipped, yeah, the orbit basis of partition diagram. So this is basically a bijection which gives which results into embedding, and so hence we prove this relation that MP lambda xi embedded into partition algebra, and you have such a relation that there will be a idempotent which satisfies this thing. And since partition algebra is cellular, and so our algebra will be cellular in that range, and semi-simplicity also follows. So this is the result, that our algebra is semi-simple when this xi is an integer and exceed 2k minus 1, and cellular over the complex number. And if you something wrong. Yeah, so if you give 2 minutes, then I can tell about the 2 more slides. Is that okay, or I should stop here?
I think you should stop it because we are right on time for the break.
Okay, no problem. Yes.
So I think I encourage everyone to ask you in the gather town, because we have the lunch break and it's going to be in gather town. So if you are around, I think people could go and ask you about those. But there are any, let's turn to Digjoy again.